All right, good morning, everyone, and it's a great pleasure to be here. So thanks for the great conference that the organizers have put on. I'm going to continue the discussion on the Milky Way and talk about recent progress on high-velocity clouds. So to begin with, this is a meeting on the CGM, and I'm talking about high-velocity clouds. So I want to get us all on the same page as what is the connection between high-velocity clouds and CGM, because I don't think this is actually obvious. High-velocity clouds are not traces of the diffuse CGM of the Milky Way or of any Milky Way-sized galaxy. They're more tracing the disk-halo interface, the region close to the galaxy. And Jess has just told us about some other recent work on this. But if you look at a recent simulation, just to kind of get started, I took this one from TNG50. The gas around a Milky Way-sized galaxy is in three basic regions, right? There's the disk, maybe a kiloparsec thick, where the ISM lives. There's this interface region of, say, 5 to 10 kiloparsecs. And then there's the diffuse CGM out to the virial radius. What the gas I'm going to talk about today is mostly in this disk-halo interface region around 10 kpc. Not all of it, but mostly that's where we're talking in terms of location. And in terms of definition, high-velocity clouds historically were defined as H1 clouds, right? H1 neutral clumps at high velocities. And high velocities means velocities that are not co-rotating with the disk. So you can think of this as the non-co-rotating gas close to the disk, but so inflows and outflows. But the point I really want to emphasize here is that they were defined as H1 clouds. So if you ask a lot of people what is an HVC, or if you read a bunch of HVC papers and you look in their introduction, they'll often start by saying HVCs are H1 clouds in the halo of the Milky Way. Fair enough, but if we were to redefine them now based on what we've learned from Hubble and other instruments, I don't think we would define them as neutral clouds. We would define them as multi-phase clouds. And multi-phase is, of course, another one of the big themes of this meeting. How do we know HVCs are multi-phase? You can look at any HVC spectrum from COS. This is actually one of the first quasars I ever worked on myself about 20 years ago. There's a complex C-site line. And I want you to look at that gray shaded absorption. There's all this different ionization. There's low ions, there's intermediate ions, and there's high ions. The high ions in particular, they're coming from gas of lower density and higher temperature. So it's multi-phase. So just from the data alone, if you look at the UV spectra, you can see that we have gas at a range of temperatures and densities. Now, there's a lot of work that's been done by different people on this ionized gas. So if you take all the Hubble directions on an all-sky map, so this is the all-sky Westmeyer H1 map. This is where the H1 is in the halo. You can put a circle wherever Hubble is pointed, and this was a big survey that Philip Richter did a few years ago. And you can look at the covering fractions. How much of the sky is covered in the high-velocity gas? And whereas H1 is about 37% covered down to the limits of all-sky H1 surveys, about 10 to the 18 or so, in the UV lines, the covering fraction is much higher. So you take a line like silicon-3, that's one of our strong UV metal lines, that covers about 3/4 of the sky. So it's very prevalent. Now, you can also ask where's most of the mass in high-velocity clouds? Is it in ionized gas or is it in neutral gas? There's different ways you can do this calculation. You can look at individual clouds and run cloudy models and so on. But I think it's also useful just to look at the totals. If you look at the sum of all the H1 mass in high-velocity clouds, you get a couple times 10 to the 7. This is from Mary Putman's review article. If you look at all the H2, the ionized gas, various groups have looked at this, including Lehner and Hauck. They find over 10 to the 8. And the point is there's a few times more ionized mass than neutral mass across the sky. So these things by mass are mostly ionized. And by the way, I haven't talked about distances yet. These numbers depend on distance, but the ratio, the distance cancels out. So this result is actually independent of distance, that the ionized mass is much higher than the neutral mass. So neutral gas is a minority part of these clouds. So what about distances? Distances have been unknown for quite a while, but I want to show a recent result from Nicholas Lehner's group looking at this, looking at high-velocity clouds towards halo stars. So we can look at these clouds not just towards quasars, but also stars, as Jess was telling us as well. Hannah Bish has looked at work like this. But we can look at the covering fraction of the high-velocity clouds as a function of distance above the plane. So in this survey, there was 55 stars, and as you go up above the plane, so-called z distance, what you notice is this covering fraction increases until you get to a certain point. And above that, the covering fraction levels off. That happens at about 7 kpc off the plane. And that's telling you that most of these high-velocity clouds are in front of 7 kiloparsecs. It's like you're looking through a cloud layer, and then at some point you're breaking through the top of the cloud layer, and there's no more gas above it. It's not all the gas. There are exceptions to this, which I'll get to, but most of the high-velocity gas is within that distance. So this is bracketing that, where they're located. And so this is why I was talking about the disk-halo interface to begin with, is that most of these things are within 7 or so kiloparsecs of the plane. And in terms of how far that puts them away from the sun, that corresponds to, let's say, 10 or 15 kiloparsecs, depending on where you're looking. So they're pretty nearby clouds. These things have a range of metallicities. I will go through this pretty quickly, but there's been a lot of work by different groups on metallicities of these clouds. And the numbers range from a few percent solar, particularly in some of these compact high-velocity clouds, which are very small clouds on the sky. They're very subsolar, very unenriched. But then you go up to things like complex C, which are like 20% or 30% solar, and some of the clouds reach supersolar metallicities. So there's a range of metallicities. And so any model that is looking at HVCs and is trying to explain where they come from has to explain why do we see a range of metallicities. And this is why it's thought to be such a complex population, is you can't just get one model that can explain all of this at a single metallicity, because the numbers are very diverse. There's more inflow than outflow in HVCs. This is a result we looked at a few years ago. And this comes from taking the Null Sky high-velocity cloud catalog in UV absorbers and splitting it into inflowing and outflowing components. And we can do this just with a simple kinematic cut. Is the velocity approaching the galaxy, or is it moving away? So we can take this population, split it into two, and then we can infer the mass flow rates of the high-velocity cloud gas in the inflow and outflow. We did this a few years ago, and we found about half a solar mass per year of inflow, a much smaller amount of about 0.16 solar masses a year of outflow. So you look at the difference, there's a net inflow of about a third of a solar mass per year in these clouds. Is that important? Well, you can look at the star formation rate of the galaxy. That's about 2 solar masses per year. So we can see about, let's say, 0.4 out of 2. So there is some inflow that we're seeing here. By no means is this all the fuel you need to match the star formation budget, but it's a decent chunk of it, right? Because this is also just in clouds at 10 to the 4 Kelvin, right? Just the stuff we can see in the UV metal lines. So this isn't including hot gas. That would add to the inflow, right? This is just in the cool photoionized gas that we see in these lines. Okay, one of the last things I want to mention is dust. And we've had some recent work on dust in high-velocity clouds. There aren't many detections of dust in high-velocity clouds because they have a low dust-to-gas ratio. In other words, there's just not much dust there compared to like ISM gas, for example. But we've been able to find some evidence. So if we take complex C, which is this big cloud up here, and we look at a background quasar, we were able to use a extremely high-quality cost spectrum of a quasar, Markarian 817, that lies behind this cloud. If there's any COS enthusiasts out there, please ask me about this later. This is a COAD of 165 exposures, where they looked at the same quasar every day for 6 months for a different program. If you add all that data up, you get incredible quality spectra with unbelievable signal to noise. So we can do a chemical composition analysis of anything along the line of sight. And that includes complex C, which happens by good luck to lie right in front of this quasar. So we did a chemical composition analysis, and we can look at the abundance of different elements in this cloud, in this halo cloud. And we find an overall metallicity of about 30% solar from oxygen and sulfur. Those are our reference elements for the metallicity. But when we look at other elements covered by our data, we find what are called depletions, right? We find sub-solar abundances of aluminium, silicon, iron, and nitrogen. So what's going on here? Well, the usual interpretation of these sub-solar abundance ratios is dust depletion. So if you just take the same data and instead of doing it relative to hydrogen, which is what an abundance is, you do it relative to sulfur, which is how we define depletions. And sulfur is taken because it's thought to be mostly undepleted. You can see how much is missing out of each element, missing from the gas phase. So you can see there's a few tenths of a dex of depletion in aluminium, silicon, and iron, and nitrogen. So the interpretation of these is a dust effect, except nitrogen is a little different. That's thought to be intrinsically underabundant. We think that's an abundance effect rather than a dust effect. But for silicon and iron and aluminium, these are the traditional signatures of dust depletion. People see these in quasar absorbers, they see these in the ISM. So we get a measure of how much dust is in, how much of these elements is in dust and not instead of gas. And that's important because it gives us a clue of where these clouds come from. Right? If these clouds came from the disk and were thrown around by fountains, or they came from satellites, we would expect some dust. But if they were infalling, if they were coming out of filaments or accreting for the first time, you wouldn't expect dust. So it's a clue to where the cloud came from. And we have future work coming up. This is an archival program led by Francie Cashman to look at dust depletion in other clouds too. There's currently 4 clouds that have some depletions, and we're going to get data for about 8 more clouds. Last thing, I want to just highlight some work by David French, who works at Space Telescope, who's looked at the column density distribution function of high-velocity clouds, so we know how many of them are as a function of column density. And for anyone modeling HVCs, please come and talk to me about this, because this is a very useful observational data set that we have. And I will finish with that and leave my summary points up. Thank you.
Any questions from the crowd? Jake?
When you talk about the dust depletion, I'm wondering, maybe you need more sample for this, but is there a difference between the stuff that's outflowing and inflowing for the dust content that you expect?
Yes, so that's a great point. We don't yet have enough data to tell, is there a observed difference between the depletions in the inflowing and outflowing. But yes, that is something that you could compare with the models of where it came from. I mean, yeah, broadly speaking, if it's recently produced, I mean, the dust is produced by stars and supernovae and GV stars. So if it was recently produced gas that was blown up, it should have dust. Yeah. So yes, if we had enough data to separate inflow and outflow, I think we could look into that more. Yeah.
So you lead on to my question is, what's the next step? Is it more data or is it better instruments or a combination?
What's the next step? Yeah, I think a combination. I think we need to figure out how the hot gas is relating to the cool gas. I mean, when I talk about inflow rates in cool gas, there could be it's probably more inflow in the hot gas, the 10 to the 6 Kelvin and above gas, than in this gas. But we don't really have enough data to connect the cool clouds around the Milky Way with the hot clouds. I mean, so high resolution X-rays spectroscopy would be awesome, just to fit together those different phases. I think that's one of the missing pieces we have. I've told you about really the cool gas content here around the Milky Way, not the hot gas. That would be a good thing. Another thing would be simulations.
So the LEM team approves of your message.
Okay, yeah, the LEM, right. But, and then also simulations. There's some amazing simulation, high resolution simulations of high velocity clouds, and we'd like to compare the data with those in more detail.
I have a question. You mentioned about the dust. So what scale of dust are we talking about? Can it be traced by like infrared, or is the dust that's like, what's the scale, all scales of dust?
So we've looked for this dust emission in the infrared and not found it. And when I say we, I mean the community. People have looked for thermal dust emission in the infrared from these clouds and generally found non-detections, just not much there. And that's thought to be because the dust to gas ratio is just so low. There just isn't much dust mass in these clouds. But the UV is so sensitive that we are able to see it through these depletions. So that's kind of why we're doing the UV dust studies, is the infrared is unable to detect the emission. Does that answer your question?
Yes.
Yeah.
Any other questions? John? Good.
Okay. So going back to the abundance pattern, the underabundance in nitrogen, as you said, it can be due to just different chemical enrichment sources. There's the primary and the secondary production. But then at the same time, you see distinct dust depletion, right? That means this gas has been relatively enriched. Is that consistent with the idea? So the underabundance in nitrogen seems to suggest to me that it's primarily due to primary production. The secondary hasn't kicked in yet.
Yes.
But at the same time, the metal enriched gas, is there a tension here? Have you looked into?
That's a great question. I don't think there's a tension, but this is exactly why we're not claiming anything based on the nitrogen. But the nitrogen looks like it can be explained by these intrinsic abundance effects, not by dust effects. But if you look at the other elements, like look at the silicon to sulfur, they're both alpha elements.
Right.
So they're both produced by the same origin pathways in stars. So if you see a difference between the silicon and sulfur, like here we see about 0.3 dex a difference, that's very hard to explain as an abundance effect because they're both alpha elements. So that's why we think that that's the one that's sort of the strongest evidence for dust. And iron as well, you'd expect it to come out similarly. Right? So I don't know if there's a tension. It's just I think both things can be happening at once. You can have these effects affecting the nitrogen abundance, but then you can have some dust depletion on top of that.
Yeah. So what I'm thinking is at this chemical enrichment level, you would have expected the secondary to kick in
Yeah.
to enhance the nitrogen, so it should have caught up. And yet you are not seeing that.
So what we haven't done yet is look at the time scales for how long
Right.
that would take.
That's right.
So that's a great thing, and we can discuss that more. Yeah, thank you.
All right, let's thank Andy and then all good.